Condition for collinearity. Welcome, everyone. Before we dive into today's new topic, let's take a moment to reflect on what we have already covered. In our previous lessons, we learned a very powerful technique, using determinants to calculate the exact area of a triangle, provided we are given the coordinates of its three vertices. Now, today we are going to explore a very specific and interesting geometric case. We are going to look at what happens when those 3 points don't actually form a triangle at all. Instead, imagine a scenario where the 3 points are positioned such that they all lie perfectly along a single, straight line. This brings us to our main topic for today, the condition for collinearity. Understanding collinearity. First, let's look at the terminology. The word collinear actually tells you exactly what it means if you break it down. It comes from the prefix co, which means together, and linear, which refers to a line. So, in the context of coordinate geometry, we say that 3 or more points are collinear if they all lie together on the same single straight line. But why does this matter for our study of determinants? Let's look at the geometric logic behind it. Think back to a standard triangle. A triangle is formed when 3 points are positioned such that they are not on the same line. This arrangement creates a two-dimensional surface, which gives us a measurable area. However, imagine a dynamic scenario. Suppose you have 2 points fixed on a line, and you take the third vertex of your triangle and start moving it closer and closer toward that same line. As the vertex approaches the line, the height of your triangle steadily decreases. Eventually, a critical moment occurs. When that third point lands exactly on the line connecting the first 2, the triangle loses its height entirely. It collapses, and what was once a triangle becomes nothing more than a simple line segment. Since a line segment has length but absolutely no width or height, the area of this degenerate triangle, as we call it in mathematics, is exactly 0. To make this even clearer, let's use a real-world analogy. Imagine you are standing alongside a perfectly straight highway, and there are 3 electric poles planted in a straight row along the road. If you tried to take a large, triangular piece of fabric and stretch it between the tops of these 3 poles, you wouldn't be able to create any kind of surface or tent-like shape. Because the poles are in a straight line, the fabric would simply lie flat, stretched tight along the line of the highway. Now that we've recalled how to use determinants to find the area of a triangle, let's dive into the core concept of this lesson, understanding collinearity. This brings us to a very important realization, which we will formalize in the next slide. If the area is 0, the points must be collinear. The mathematical condition. Suppose we are given 3 specific points, labeled P1 with coordinates x1, y1, P2 with x2, y2, and P3 with x3, y3. As we discussed in our previous lesson, we can calculate the area of the triangle formed by these 3 vertices using a determinant. Specifically, the area is equal to 1/2, multiplied by the determinant of a 3x3 matrix, where the first column contains our x-coordinates, the second column contains our y-coordinates, and the third column is simply a column of 1s. Now, here is the crucial part for our topic today. For these 3 points to be considered collinear, we just established that the triangle must have no area. This means the area must be exactly 0. So, we set our formula for the area equal to 0. This gives us the condition where 1/2 multiplied by that same 3x3 determinant equals 0. But we can make this even simpler to work with. Since we are dealing with an equation set to 0, multiplying both sides by 2 won't change the truth of the equality. Therefore, the simplified mathematical condition for collinearity is simply that the determinant itself must equal 0. In the next few slides, I will show you exactly how to apply this determinant to solve problems step by step. Now that we understand the geometric intuition, that a triangle collapses into a line when its height becomes 0, let's translate this concept into a precise mathematical formula. Step-by-step process to check for collinearity. Now that we understand the mathematical theory behind why the area becomes 0 when points align, let's talk about the practical application. I want to give you a clear, step-by-step roadmap so you can approach any problem of this type with confidence. First, your very first step is to identify the coordinates. When you are given a problem, clearly list out your 3 points and label them as x sub 1, y sub 1, x sub 2, y sub 2, and x sub 3, y sub 3. Keeping them organized right from the start prevents confusion later on. Second, you need to set up the determinant. You'll take those coordinates you just listed and arrange them into a 3x3 matrix. The first column will be your x-coordinates, the second column will be your y-coordinates, and the third column, this is very important, will be a column of ones. Third, you must expand the determinant. You'll calculate the numerical value of this matrix, typically using the expansion method along the first row, just as we have practiced in our previous lessons on determinants. Finally, the most crucial part, analyze the result. Once you have your final number, look at it closely. If your result is exactly 0, then you have proven that the points are collinear. However, if you get any value other than 0, it means the points do not lie on a single line, and instead, they form a triangle with a measurable area. In the next slide, we are going to put this exact 4-step process into practice with a worked example to see it in action. Worked example. Our problem today is to determine whether these 3 specific points, A with coordinates 1, 1, B with coordinates 2, 3, and C with coordinates 3, 5, are collinear. To solve this, we'll follow the process I just outlined in the previous slide. First, step 1, we identify our coordinates. We have x1 equals 1, y1 equals 1, x2 equals 2, y2 equals 3, and x3 equals 3, y3 equals 5. Step 2, we set up our determinant. Based on the condition we learned earlier, we need to check if the determinant of a 3x3 matrix, where the first column is our x values, the second column is our y values, and the third column is all ones, is equal to 0. So we are checking if the determinant of the matrix with row 1, 1, 1, 1, row 2, 2, 3, 1, and row 3, 3, 5, 1 equals 0. Step 3, now we expand this determinant along the first row. Be very careful here with your signs, as I'll mention later in the presentation. We take the first element, 1, and multiply it by the determinant of the 2x2 matrix remaining when we cross out its row and column. That's 3, 1, 5, 1. Then, we subtract the second element, which is 1, multiplied by the determinant of the 2x2 matrix with 2, 1, 3, 1. Finally, we add the third element, 1, multiplied by the determinant of the 2x2 matrix with 2, 3, 3, 5. Step 4, let's calculate these 2x2 determinants. For the first part, 1 times the quantity 3 times 1 minus 1 times 5. For the second part, we have negative 1 times the quantity 2 times 1 minus 1 times 3. And for the third part, 1 times the quantity 2 times 5 minus 3 times 3. Let's simplify that. This gives us 1 times the quantity 3 minus 5, minus 1 times the quantity 2 minus 3, plus 1 times the quantity 10 minus 9. Continuing the simplification, we get 1 times negative 2, minus 1 times negative 1, plus 1 times 1. This simplifies further to negative 2, plus 1, plus 1. When we sum these up, the final result is exactly 0. So, looking at our conclusion, since the value of the determinant is 0, we have mathematically proven that the points A, B, and C are indeed collinear. They lie perfectly on the same straight line. Now that we have understood the theory and the step-by-step method, let's put everything into practice with a worked example. Key takeaways. First, let's revisit our core definition. Points are considered collinear if they all lie together on the exact same straight line. As we discussed earlier when looking at the geometry of triangles, there is a vital geometric link here. Remember how we saw that moving a vertex closer to the base reduces the height? Well, when those points become collinear, the triangle essentially collapses, meaning collinear points form a triangle with an area of exactly 0. Finally, let's consolidate the mathematical condition we've just mastered. To mathematically prove that 3 points, with coordinates x sub 1, y sub 1, x sub 2, y sub 2, and x sub 3, y sub 3 are collinear, we use the determinant method. The condition is that the determinant of the 3x3 matrix, where the first column is the x-coordinates, the second column is the y-coordinates, and the third column is all ones, must equal 0. All right, let's wrap everything up by reviewing the key takeaways from today's lesson. Keep these 3 points in mind, because in our next slide, we'll look at some common pitfalls to avoid when performing these calculations. Common mistakes. First, let's talk about ignoring the third column. When you're setting up your determinant, it is very easy to get caught up in the x and y coordinates and completely forget to include that third column of ones. Remember, without that column of ones, you don't have a 3x3 matrix, and the entire method for calculating the area fails. Always double-check that your matrix is a complete 3x3 structure. Second, watch out for sign errors during expansion. This is perhaps the most frequent mistake I see. When you expand your determinant along the first row, as we did in our worked example, you must remember to alternate your signs. It follows a plus, minus, plus pattern. Specifically, the sign of the middle term, the element in the first row, second column, must be flipped. If it's a positive number in the matrix, you must subtract it during expansion. Finally, try not to confuse collinearity with parallelism. While both terms involve lines, they describe different things. Collinearity is about a single set of points lying on the same line. Parallelism, on the other hand, refers to two separate lines that run in the same direction and never intersect. The determinant method we have learned today is specifically designed to check if points are collinear by looking for a zero area. Now, before we wrap up today's lesson, I want to pause and highlight a few common pitfalls. Even if you understand the concept of collinearity, these small errors can lead to incorrect answers in your exams. Keep these tips in mind, and you'll be able to approach these problems with much greater accuracy. Great job today!